Ladies and gentlemen, welcome back. We are going to look at problem number 2 on the review. Problem number 2 is what I like to call basically the lab. So it's recalling everything that we've done in the lab in order to solve this. First thing, in order to do this, I always like to draw 3 force diagrams whenever I have 2 objects. So you'll notice that the first 2 force diagrams are easy. I'll draw one of the box and one of the cart. The last force diagram is always going to be a combo force diagram, kind of including both of them in our system. So again, you'll notice the same routine that I followed before. I'm just going to write down all my systems. The first system I'm going to look at is just the hanging mass. And in this system, first off, I know there's an FG going down on the hanging mass by Earth, and I know there's an FT going upwards. I know the FT must be less than the FG. Why is this true? Because I know the cart is hopefully accelerating to the left. Because the cart is accelerating to the left, the hanging mass must be accelerating down. FT on the hanging mass by the rope. So that's that. FT is larger than FG. You can see that in that diagram. Next system is going to be the cart. In this situation, if I'm going to look at the cart, on the cart we have an FN going up on the cart by the ramp. We have an FG going down on the cart by Earth. I know those 2 are equal because they're balanced and it's not accelerating up or down. I also know that they're equal because the rope is pulling directly horizontal. So it's not pulling up like we saw in problem number 1. And so that's our FT on the cart by the rope. And we have FFK going to the right on the cart by friction. Oh, wow. Oh, hamburgered myself. On the cart by the table, or the ramp in this case. Friction's not an object, Mr. Z. Duh. It's been a while. So, this is our situation right here. The other thing that I like to note is this tension force is equal to this tension force because of ropes. All what they do, pulleys, all what they do is redirect forces. And because it is the same rope, we know the tension in that rope has to be the same. So let me make those 2 dashes so we're not confused. And then my famous force diagram of them both. Oh, I love this one the best. Cart and the mass. Hanging mass, I guess you can call that. And when we combo them, remember anytime that you combo 2 of them, that force pair or those forces that are in equal and opposite directions, in this case, because the pulley redirects that force, these tensions will be in opposite directions. They disappear. So we are left with this. We have an FN on the cart by the ramp. We have an FG on the cart by Earth. We have a frictional force, FFK, on the cart. This is still on the cart. It's not by the system. The friction is only affecting the cart. It is not affecting the hanging mass. So I just like to point that out. On the cart by ramp. And the last one is going to be now the FG on the hanging mass by Earth. And so what I always like to point out is we're looking at every outside object that is acting on our system. So the Earth is technically, in this case, pulling the hanging mass to the left because the the pulley has redirected that force. If that confuses you, go back to the pre-lab. We did a whole explanation on how those force diagrams worked. These 2 are still equal to each other, but I want you to note the FN, the table, or the ramp in this case, is only pushing the cart upwards. It is not pushing the hanging mass. So you'll notice that my system there is not cart and the hanging mass, it's just the cart. Friction is only affecting the cart. It is not affecting the hanging mass. directly. So we have that in this situation. And this FG going down is just on the cart. Keep that in mind. It is not pulling the hanging mass down because the rope is, again, redirecting that. So those are our 3 force diagrams, and you're going to notice a couple of things very quickly. I know the mass of the car, and I know the mass of the hanging mass. First things first, I probably look at this, and I'm like, I don't know these tensions right out of the gates, and that frustrates me because normally if I know those, I can then go through and quickly solve for the accelerations, but I don't. And so that really, once you don't know one of the forces in a force diagram, if that force is causing the acceleration, or it's one of the forces that is a combo in terms of causing the acceleration, you can't do anything with it. So I kind of say those two are probably not good places to start. However, I go on over here and I realize I have FG, which I know, right? FG on the hanging mass, I can solve that, and I have FFK, which I can solve for as well. So all that this takes is a little bit of situations where I always start with A is equal to the net force over the mass of the system, and I go from there. Let me just go back and make sure. What does it ask for? Oh, the acceleration of the car. Perfect. So I go on over here. Net force is, in this case, equal to FFK minus FG on the hanging mass divided by the mass of my system. Mass of my system is the mass of the cart and the hanging mass. So in this situation, I would go back on over here and I'd say, all right, what's true about that? That would be 1.6. So in this case, I'm going to put 1.6 kilograms down there. And FFK, I would actually have to solve for FFK. How would I solve for FFK? And take mu, gives us 3.92. And FFK, if we had to solve for FFK, that is equal to mu k times Fn. We know mu k is 0.1. Fn in this example is 9.8 newtons per kilogram. So we see Fn on the cart by the ramp. That is equal to this Fg on the cart. So we would take 9.8 and we multiply it by 1.2 kilograms. Come back here. So we do 1.2 times 9.8 times 0.1, and we get 1.176 newtons. And if we subtract this right here, divided by 1.6, we will get an acceleration. And that acceleration will be negative. Why would it be negative? Because the cart, or our system, is accelerating to the left in this case from the cart's perspective. So that is how you get the acceleration, and then the rest of this problem is all basically unit. Well, in this part B is going to be unit 3. So now in part B, we know the acceleration that is given from above. We know that delta x in this situation is going to be, let me go back and see, delta x in this situation is 20 centimeters, so that would be 0.2. In this situation, the way that I'm thinking about it is the cart starts here, and the cart will end here. So if this is my initial and this is my final, I'm seeing that as a negative displacement, so I'm going to call that a negative 0.2 meters. And I know that my initial velocity is 0 meters per second. Once I know 3 of those, I'm basically on my way in order to solve for the time. The equation that you would use using these 3 and solving for time is going to be delta x is equal to 1/2 at squared plus v naught t. You'll notice v naught t is 0 because your initial velocity is 0. And you're looking at a negative value here and a negative acceleration, which will allow you to get the square root. You'll notice if you did not put the negative 0.2 in there, you're going to be trying to take the square root of a negative number, which will probably frustrate you and tell you that you have an imaginary piece. But again, if you're thinking about it accelerating to the left, you also have to think that it's going to displace to the left, which is why that negative 0.2 fall into play. Notice that I transferred it into meters as well. Remember, if you're dealing with centimeters and you're trying to do meters per second squared or anything else like that, you're going to run into problems there. So that is how you'd solve for part B. And part C asks for the the tension in the rope. Because now you know the acceleration, you can go back to either one of these situations and solve for the net force. So if you were to do that, I'm just going to give you a situation with the hanging mass. I now know the acceleration, and so I can set up my net force equation. A is equal to net force divided by mass of the system. Acceleration I know. Mass of the system I know too. The only difference is now the mass of the system is going to be the mass of whatever my system force diagram is. So you're going to notice that I am going to be using the hanging mass. And I believe that the hanging mass, if I could stop doing that, that would be nice. The hanging mass in this situation is how much again? 400 grams. So again, I would translate those into kilograms like that. And again, I would take Ft minus the Fg on the hanging mass. And you're going to notice that I have enough information. I can solve for that. That I know. And of course I know the mass, so I can get my Ft. I always like to say double check to make sure that you could get that Ft equal to that Ft. Those should be equal to each other, so I'd say double check. That is how you know that you've done it correctly. So that is problem number 2. If you have any questions about that, don't hesitate.